Statisticians on parade. What'll we do? What'll we do? My teacher is creepy as. Actually, I'm not kind of liking the words that I can come that would rhyme, but let's think about that later. Right now, we are going to do a one sample proportions test. And here's the idea. We sample a whole bunch of statisticians and we say, are you left-handed or right-handed? So first off, are we talking numerical or categorical? They're going to say right, right, left, right. What's the average? No, we don't talk about average. This is proportions, which is why it says it's a test for P, which is kind of a spoiler, but I don't know how to get rid of that now because I've already started recording. We want to test if less than 15% of the statisticians are left-handed. So what's my null and alternative? It said less than 15%. There's no equal sign, so that has to be the alternative. The null would be greater than or equal to. We're going to use an alpha of 0.05 just because I'm still trying to think of a good rhyme for the word do, and I didn't want to think about it. So, next question, is this going to be Z or T? If it's proportions, it's always Z. There is no T associated with proportions. Here's the way we used to do these. We took our observed data minus our mu. There's a glare right there. That's really annoying. And then we have our sigma over the square root of n. Well, it's still going to be Z. But now, instead of x bar, we're talking about our proportion from the data. That's p hat is what we use right there. And we're going to subtract the parameter, which we think is p. And we're going to divide by the square root of p 1 minus p over n. But which p? Are we going to use p hat or are we going to use p? And the answer is you want to always use the best value that you have. And in this case, we have a parameter. That's the best thing we can use. So it's going to be p1 minus p without the hats over n. Here's x bar minus mu divided by, here's our new sigma over the square root of n. So same method, just a little bit different equation. Here's what the picture looks like. Here's the picture where we center it over the proportion that we believe is true. It's stuck like glue. Not on my shirt, which is blue. And here is our standard deviation, square root of 0.15 times 1 minus 0.15 over our sample size, which is 150. That's this guy. And here's where our 16 over 150, that's our proportion that we got from our data. How did I know it landed right there? Spoiler alert, I actually did the z-score while you weren't looking, and that helps me. So how am I going to get the z-score? I'm going to take this value right here, which is 16 over 150, minus the parameter that I think it is, which is 0.15, and divide by this guy. This should feel like the normal distribution probabilities we did weeks ago. We have x, mu, and sigma. 0.15, 1 minus 0.15 over 150, and I already looked it up. It is negative 1.49. That's our z-score. From there, are we going to want the area to the left, to the right, or in both tails? I'm going to look right here. It's a less than, so I want the area to the left. Now, I'm not a great artist, but just eyeballing it, it looks to me like this is about 0.05, and I think I am not in the rejection region. But sometimes I get wrong just because I'm not a great artist, so let's see what the atlas says. So I'm going to put in my z-score, which is negative 1.49, and I want the area to the left, which is what we already thought we knew through this view of all two. It can't be that hard to rhyme us. Our p-value is larger than alpha, which is what I thought. But I gotta admit, it's a lot closer than I thought it was gonna be, so that's why you always double check, even though sometimes with a picture you can get a good clue. Clue? So, now I'm going to fail to reject, which we conclude the hand's true percent may include the 0.15. So we do eschew a few of the true view, thank you. I think I'm kind of out of rhymes now.